I would like to sincerely thank all the committee members for taking time off their busy schedule to attend my PhD thesis defense exam, titled Effects of Advanced Material Morphologies on Thermal, Electrical, and Thermoelectric Properties. So before discussing about my PhD work, I would just give a brief overview of my 5 years academic journey. So we had a chance to publish research articles in considerably good journals, including Nature Communications. And we are recently invited to write a book chapter in Advances in Heat Transfer related to machine learning applications in heat transfer. I also had opportunity to represent ASU at several reputable conferences, including MRX, ASME, and IEEE. And we also had opportunity to represent ASU in one of the heatsink design competitions in which we were finalists. So it has been quite a journey so far. So coming back to my thesis topic, why we need advanced materials in the first place. There's a chat there. So if you look at the US energy consumption in 2019, on the left side, we can see that what fraction of the total energy is generated by various sectors. And on the right side, we can see how much of the total energy is consumed by different sectors. But on the extreme side, we can see about 68% of the total generated energy is wasted. So, and globally, this number is about 80%. So there is really a need of improving energy conversion and transport mechanisms. And we believe that the practical realization of advanced materials could help us reduce the wasted energy. So there is all the manufacturing limitations has always posed a grand challenge in realizing the true potential of advanced materials. The process of converting traditional materials to advanced ones involves several drilling techniques to improve functionality in plain field and alloyed materials. However, morphology control limitations has always restricted to realize the true potential of advanced materials. However, with recent advancements in fabrication and additive manufacturing, researchers have now better control over the morphology in advanced materials, and that could basically unlock the true potential of advanced materials. So there is really a need of developing design methods that can provide insight into morphology control recommendations in advanced materials for enhanced thermal, electrical, and thermoelectric properties. Oh, okay. To investigate microscale morphologies, carbon nanotube or CNT-based composites can be analyzed, and we can see how the CNT morphology can affect the transport properties through the microstructure. And more specifically, carbon nanotube composites are widely studied as considerable efforts are being made to replace copper in high power density devices. And furthermore, we can also analyze the CNT morphology effect in carbon nanotube fibers to study the transport properties. For macro scale morphologies, there are several examples out there, from foam heat sinks to passive coolers and thermoelectric generators. But to specifically study the thermoelectric properties, we can take the example of thermoelectric generators. And we can attempt to answer how can we achieve better thermoelectric properties and mechanical strengths by manipulating the morphologies in thermoelectric devices. So my thesis is divided into 7 chapters, and each chapter attempts to answer some important research questions that may contribute in the advancement related to these devices. Chapter 2 and 3 are dedicated to thermoelectric devices. Chapter 4 and 5 are dedicated to investigating microscale morphologies in CNT-based composites. And chapter 6 is dedicated to studying morphology effect in CNT fibers. So starting from chapter 2, which is 3D printable thermoelectric devices. So as we all know that thermoelectric generators have relatively low power generation efficiencies and mechanical strengths. And this is due to the fact that majority of the thermoelectric devices are fabricated in simple cuboid shape. And this simple cuboid shape do not allow us to effectively control the temperature gradient across the leg and also maintain higher electrical conductivity at the same time. And another, most importantly, the mechanical strengths of these cuboid legs are very low and they are very brittle, and they are not suitable for high vibration environments. So the question here is that we need to come up with different and complex TE morphologies that may provide us better thermoelectric properties and mechanical strengths. And for that purpose, Dr. Son at UNIS developed a novel 3D printing technique with which you can fabricate any shape of thermoelectric devices using copper selenide ink. So I will just quickly play the pen. So we start off by printing the first layer of the material, and then we deposit another 28 layers on top of it. And in the end, we deposit the 30th layer. So using this printing technique, you can basically fabricate any shape of thermoelectric leg. But the question here is that what kind of shapes should we print with it that provide us higher thermoelectric properties and mechanical strengths? To answer that, we can get inspiration from naturally occurring architectures such as honeycomb structures, which have relatively higher mechanical strengths. They provide better control over the heat transfer. And most importantly, they are very strong at relatively low densities. So we can take inspiration from these architectures and try to print the thermoelectric legs in the honeycomb as a honeycomb structure. But we have to understand what's the underlying physics behind it if we are getting better properties using this architecture. So for that purpose, we developed a three-dimensional finite element model using the multiphysics of thermal and electric current modules. The most important parameter in a thermoelectric leg is the aspect ratio, which is the ratio of leg length to its cross-sectional area. This is important because for cuboid shape, whenever you change the aspect ratio, there is always a trade-off between the thermal resistance and electrical conductivity. So using FEM, we estimated the power outputs at different aspect ratios for different outside temperatures. And we see that for the aspect ratio of 1.5, we get the maximum power outputs. And we assume that this aspect ratio will be ideal for any shape using copper selenide ink. So using FEM, we estimated the generation efficiencies of cuboid, hexagonal, and honeycomb architectures. At lower temperatures, we don't really see much difference in the efficiencies, but at higher temperatures, we can see that the hexagonal column provides us 22% more efficiency, and the honeycomb architecture provides us 26% more efficiency than simple cuboid shape. And to understand why is that, we need to look at the temperature difference plots and the heat flux maps. So for the same temperature difference across the leg, the inefficient heat spread in the honeycomb architecture basically gives rise to more thermal resistance, and that consequently gives us more larger generation efficiency. We also use FEM to estimate the mechanical strength, which came out to be around 200 megapascals. And if you look at the HP Gibson plot, when you reduce the effective densities, your compressive stiffness decreased by this relation, E over rho exponent 0.5. But for the honeycomb architectures, we can see that the compressive stiffness compared to the relative densities is about 2 factors more than the HP Gibson relation. And the relative densities are in the range of 600 to 1,000 kg per meter cubic, which is about 25% less than the cuboid shape. So this makes this thermoelectric architecture suitable for applications where lightweight and high strengths are needed. So in conclusion, how can efficiency and mechanical strength of thermoelectric legs be improved? We answered it with our publication back in 2021. So in conclusion, We use novel 3D printing technique to fabricate complex DE morphologies that provided us 26% more power efficiencies, and also and they were found to be 25% less dense compared to cuboid shape. For chapter 3, which is 3D printable compositionally segmented TE legs, which is the extension of the previous work. So why we need segmented legs in the first place? So if you look at the temperature distribution in a simple cuboid shape, we see something like this. And if we look at the figure of merit or ZT values for different compositions of the same material, we see that the ZT values vary with the temperature. So the idea here is that what if we stack up these materials in such a way that we utilize the maximum ZT values at the corresponding temperatures within a single thermoelectric device? So again, Dr. San, they developed another 3D printing method with which they can print segmented TE legs. So I will just quickly play the demo. So we start off by depositing the first layer of first ink. Then we deposit another 10 more layers. We change the ink, we deposit the first layer. And we deposit 9 more layers. We change the ink again, deposit the first layer, and then deposit 9 more layers. So using this printing technique, you can basically print segmented TE legs, but we have to verify if this segmented TE leg is better than a TE leg when it uses just a single material. So to do that, we performed three-dimensional finite element analysis. And the researchers as units, they performed experiments with the setup that looks something like this. But another task we also perform is that we try to figure out what should be the ideal length of each segment so that we utilize the maximum power output from each segment. So for that, we performed parametric analysis, and we found out that, so in each case, we fixed the length of one segment and we changed the ratio of the other two segments. And we found out that the length of the first segment should be greater than the second segment, and the length of second segment should be greater than the length of third segment. However, due to printing limitations and for the sake of simplicity, they ended up printing the TE leg with the same length of each segment. So we use FEM to estimate the power outputs, and they perform the experiments. And we see a very good agreement between our numerical simulation results and their experiments with an accuracy more than 90%. At lower temperatures, we don't really see much improvement between segmented and single leg. But at higher temperatures, we see that segmented legs provide us 30% more power output compared to single material. And we also compared the efficiency of segmented TE leg with other previously reported works. And we found out that our segmented TE leg provided a record high efficiency of 8.7%, which was a good, significant achievement. So for our thesis question, how to maximize the performance of TE generators with multi-materials, we answered it with our publication in Nano Energy back in 2021. And in conclusion, we use 3D printing technique to fabricate segmented TE legs that provided us record high efficiencies of 8.7%. So the next chapter is regarding 2D FEM for copper CNT composites. So as we all know that for a long time, copper CNT composites are fabricated using powder metallurgy. And powder metallurgy inhibits us to get CNT fractions above 20%. Another drawback of powder metallurgy is that you really don't have any control over the CNT morphologies. And you get some entangled and clustered networks of CNTs. And they basically seriously deteriorate the properties, transport properties through the microstructure. So with the discovery of electrodeposition for CNT-based composites in 2008, we can see that researchers were able to achieve higher CNT fractions, up to 65%. But most importantly, they were able to have aligned CNTs which were near ideal morphologies of CNTs, that is straight and aligned CNTs to the field direction. So electrodeposition solved majority of the challenges, but there still remains one challenge, which is how to obtain superior properties of composites compared to copper at room temperature. As we all know that the single wall CNTs, theoretically, they are 10 times more thermally conductive and 100 times more electively conductive than copper at room temperature. So when we look at different factors in a copper CNT composite, we see that there are a lot of parameters that affect the transport properties. That is, what's the CNT morphology, what's the CNT fractions, and how CNTs interact with each other, and what's the matrix CNT interface resistance. So we need a comprehensive model that can take account of all these factors at the same time. So for that purpose, we developed a two-dimensional finite element model by extracting a 2D axial plane from a 3D composite. We agreed that the 2D approximation may not be as accurate as 3D simulations, but it allows us to generate stochastic CNT networks with CNT fractions up to 80%, which was not possible before. So when you look at a 2D composite model, you see there are three types of contacts in the copper CNT composite. Type 1 contact arises due to the interfacial resistance between copper and CNTs, as they have different work functions, and also they have imperfect adhesions. Type 2 and type 3 contacts arise due to side-to-side and end-to-end contact of CNTs. And this basically arises due to the van der Waals interactions between closely spaced CNTs. And if you look at the literature, we can basically estimate the ranges of these resistance values. Again, I would mention here that these interfacial resistance values are without any surface activation, or there's no doping materials. So we use 6 different fractions of CNTs, and for each fraction, we generated 10 stochastic CNT networks. I'm just showing example for 4 fractions, which is 5%, 20%, 50%, and 80%. For the boundary conditions, we applied potential difference and thermal gradient across the ends of composites, and we also prescribed the copper CNT and CNT interfacial resistance in these ranges. So using FEM, we can basically visualize the transport mechanism through these microstructures. And if you look at the current density streamlines, when the interface resistance is well regulated on the left side, we see that the current tends to flow through CNTs, as CNTs are highly conductive and they offer least resistive path through the microstructure. This is more easily visible in higher fractions. You can see that the current literally jumps from one CNT to another CNT. On the contrary, when the interfacial resistance are poorly regulated, we see that the current tends to flow through the copper domain. And you can easily visualize for higher CNT fractions, as current tends to bypass the CNTs and flow through the copper domain. The temperature heat flux streamlines are analogous to current density streamlines, so I'm not showing them here. So using the empirical relations, we calculated the effective thermal and electrical conductivities. So on the left side is the effective electrical conductivities, and on the right is the effective thermal conductivities as a function of CNT volume fraction and copper CNT interfacial resistances. So as we can see that if the copper CNT interfacial resistance is well regulated, adding CNTs has a desirable effect, and that basically improves the overall effective conductivity of the composite. On the other side, if the copper CNT interfacial resistances are poorly regulated, we see a monotonic decrease in the conductivities as you add more CNTs into the microstructure. So for our thesis question, what is CNT morphology and interfacial resistance influence on CNT-based composites? We answered it with our publication in Materialia Journal back in 2022. And in conclusion, we developed a two-dimensional finite element model that basically provides us insight into the flow physics, current and heat flow physics in the microstructure. And we see that if the interfacial resistances are well regulated, below 1 kilo ohm ranges for electrical and 10 exponent minus 7 meter square Kelvin per watt for thermal, it is possible to achieve superior conductivities compared to copper. However, again, this is for the ideal morphologies of CNTs, which is quite not possible yet. So chapter 5 is the extension of chapter 4, which is data-driven models for copper CNT composites. So why we need a data-driven model in the first place? So using FEM to simulate one design of composite with CNT fraction of 80%, we spent around 400 minutes using 2.2 gigahertz 6-core processor. And if we are required to simulate, let's say, 100 designs, it can take forever. So the other modeling techniques for CNT-based composites are limited by their nature and also limited in parameter space search and incur very high computational costs. But with machine learning, you can basically explore large design space at relatively low cost. Although, sure. So let's say if you want to see if I want to use CNT fractions from 10, 20, 30, 40, 50, it will basically take, you will have to simulate each and every design. And there would be other parameters, let's say interfacial resistances. You want to simulate more ranges of interfacial resistances. Then it will take, you will have to simulate basically all the designs. Yeah. So as I said before, finite element analysis, if we use it for one design, it takes 400 minutes. And later on, we will see that once we train the machine learning model, it takes less than 1 second to do the same thing. So, yes, exactly. It's not physics informed model, it's basically data driven model. So you are not doing any simulations within machine learning. You are just generating training data for it. So as I said, so generating the training data would be expensive, but once the machine learning model is trained, you will have to basically, you can search large parameter space at low cost. So for research methodology, in this chapter, we first generate the training data using already made FEM model. In chapter 4, we process the training data and then we train the convolutional neural networks with it. And in the end, we compare the FEM predictions with CNN approximations. To process training data, first we obtain the composite layout images for with the corresponding conductivities. We convert the layout, copper CNT layouts into single channel layouts to reduce the image size. And after that, to identify different interfacial resistances, we color code the background of the matrix to with 4 levels of black color. And then to basically augment the training data, we perform image transformation technique by flipping the original image horizontally, vertically, and diagonally. So that's how the CNN architecture looks like. At the input layer, you provide the copper CNT layout images, and you basically pass it through 5 hidden layers. And at the end, you form a one-dimensional feature vector, and that can be used to establish the regression model at the output layer. To tune the hyperparameters, we calculated coefficient of determination for both training and validation data set. And we changed the depth of CNN architecture by varying the number of neurons in each layer systematically. And we can see that for case 4, we get the highest coefficient of determinations with a reasonable computational time. We optimize other training parameters such as optimal learning rate, minimum batch size, and dropout layer probability. So after training CNN, we compared FEM predictions with CNN approximations, and we see that the R-square values are more than 0.98 for both electrical and thermal conductivities. So as we were discussing before, the average time for any design in FEM takes around 155 minutes. But once we train the CNN in about 3 minutes, CNN can make rapid and accurate approximations in less than 1 second. So in conclusion, for our thesis question, how to make rapid composite design recommendations, we answered it with our publication in Nature Scientific Reports back in 2022. We also presented our work in MRS conference. So in conclusion, we developed a data-driven model for approximating conductivities in copper CNT composites. And this data-driven model can be used to make rapid design recommendations to industrialists for fabricating advanced composites. And finally, chapter 6 is about pseudo 2D FEM for CNT fiber. So why we need CNT fibers in the first place? So with the recent advancements in CNT synthesis and handling methods, carbon nanotube fibers are competitive to carbon fibers and copper in terms of mechanical strength, thermal conductivities, and electrical conductivities. So researchers are actively trying to improve the CNT synthesis methods and to unlock the true potential of carbon nanotube fibers. So as we all know that the most common CNT synthesis method is solution spinning method, but it has its shortcomings. That is, it lacks the ability to control the CNT alignment, packing density, purity, and length of or size of individual CNTs. And this consequently leads to the generation of voids, intrabundle and interbundle voids, and they seriously deteriorate the transport properties through the CNT fiber. So recently, Dr. Kim, a research group at KIST, they optimized the solution spinning parameters, and they were able to obtain void fractions as low as 0.08%. And also, they also optimized the draw ratio so that they were able to achieve, basically achieve straight and aligned CNT morphologies within the CNT fiber. And the resulting CNT fiber were almost circular in shape. So this gives us an opportunity to understand how the transport properties are affected by intrabundle and interbundle voids, and how the aspect ratio of individual CNTs affect the transport properties. So for that, we developed a pseudo FEM model. Obviously, if you want to simulate a very high aspect ratio model, it can take forever due to tremendous computational demands. So to do that, we have to make certain approximations. The first approximation we make is that all the irregular shaped CNTs within the bundle are in hexagonal shape, and all of the CNTs are single wall CNTs. This allows us to basically reduce the model generation time and also allow us to control void fraction more easily. The second approximation we make, which is very crude approximation, is that the two adjacent rows of CNTs have same axial distribution. And we can basically take these two rows of CNTs and use a 3D FEM model to model the transport properties by changing the CNT-CNT interface resistance and void fraction. And then we can use this two-row CNT fiber as a single CNT in a 2D model. And we also consider the actual CNT distribution along the fiber axis. So when you place CNT bundles in the axial direction, obviously you are going to get some inter and intrabundle voids. To model those voids, we use the same exact method we use for copper CNT model, that we add a resistive element between two CNTs if the interspacing is less than 1 nanometers. So the important thing here is that since it's a large aspect ratio model, we need to make sure it is the results are computational size domain independent. And for that, we have two cases. In case one, we fix the length of the fiber and change the width. And we try to find out when the conductivities do not fluctuate much by changing the domain size. And using the width from case one, we use it in case two and change the length of the fiber. And we try to see that when the conductivities don't fluctuate much with the domain length. So we found out that for a domain width of 40 nanometers, you need to have at least 4 times, you need to have domain length of at least 4 times the length of individual CNT bundle length. So, okay. So using FEM, we estimated the effective conductivities, effective electrical and thermal conductivities for the various aspect ratios of CNTs as a function of CNT-CNT interface resistance and intrinsic CNT conductivities as well. So obviously, when you decrease the aspect ratio of CNTs, you are going to get more voids in your fiber. So as the number of voids increase, your conductivities will decrease. That's very generic. And this is for the case if your CNT-CNT interface resistances are not well regulated. But if you have very well regulated CNT-CNT interface resistances, you see a decline in the conductivities, but not as drastic as you see it with the poorly regulated interface resistances. So in the interest of time, I will just skip it, but a trend for the thermal conductivities is very similar. So to answer our thesis question, how CNT-CNT interaction affects transport mechanisms through CNT fiber, we developed a pseudo 2D FEM model that can basically incorporate CNT-CNT interfacial resistances and single wall CNT aspect ratios. So to conclude my talk and the impact of my PhD work, so for the first time, we used novel 3D printing technique to fabricate complex morphologies of TE legs that provided us 26% more power outputs. And we also fabricated segmented TE leg that provided us record high efficiencies of 8.7%. For 2D, for copper CNT composite models, we developed a 2D FEM model that simultaneously considers the stochastic CNT distribution, CNT fractions, and interfacial resistances. And along with that, we developed a data-driven model that can provide rapid and accurate approximations of the transport properties through the microstructure. And finally, we developed a pseudo FEM that can basically simulate large aspect ratios of CNT fibers. So the possible future work that can be extended from my work. So now we can basically fabricate any shapes of TE legs. And that unlocks the opportunity to topologically optimize these legs. And we can get the maximum thermal efficiencies, thermoelectric efficiencies, maximum strengths, and we can also find out their applications where the low weight and high strengths are needed. For copper CNT model, obviously we use numerical simulations to train the data, but with slight modifications, with the slight modifications in pre-processing layers, we believe that we can use actual bulk composite images to train the data and approximate conductivities in real samples. Obviously, that will require us to collaborate on large scale to generate the training data for these composites. And in the end, as the world is quickly shifting to AI-based solutions, we can educate young engineers about the potential of machine learning in mechanical engineering-related research problems through webinars or tutorials, etc. Thank you for your time, and if there is any question.